All right. Hello, everyone. Welcome to today's Corundum developer meeting for the last one of February. All right, so let's get the ball rolling here. So two main points here. OFC is coming up, and then I got some status updates. So OFC, I'm not sure if you guys are aware, is the Optical Fiber Communications Conference. Takes place in, well, various places, but past few years it's been in San Diego. All sorts of vendors related to optical communications and networking, including AMD, Xilinx, Intel, Molex/Bitware, Cisco, Arista, vendors like, let's see, Keysight Technologies. I got the bag here from last OFC. So all sorts of interesting stuff. If you're going to be in the San Diego area, March 5th through 9th, definitely recommend checking it out. The floor show is free, so definitely recommend it. So I'm going to be attending that. Let me know if you're going to be there and you want to cross paths at some point. And if you are going to be there, you might be able to do like a lab tour or something at UCSD. So it's just a couple of stops down the trolley line. Yeah. So that's the announcement for OFC, and let's go ahead and get on with the status updates for Corundum. So we got standard checkup on bugs that we're working out. FIFO memory inference issue. Get back to that in a minute. Priority flow control, AXI virtual FIFO, then switch version of Corundum, and then there's a bunch of stuff that's a little bit more kind of brainstorming at this point. There were some questions about, how to do a couple things with the Zinc devices. One in terms of providing potentially some additional application section interfaces, and then also how to use both the ARM cores and PCI Express with Corundum at the same time. And then finally, I've been doing some thinking about some potential deeper changes to Corundum, one of them being consolidating the queue management components. So some more details on that in a couple of slides here. All right. So first up, the FIFO memory inference issue. This is a problem that we noticed with Cordis, where you're occasionally getting some strange behavior in terms of the checksum offloading, and it was traced to what appears to be some inference issues with MLabs. And I think this was reported to Intel. As I recall, this latest status on this is that Intel was saying basically try it out with the latest version of Cordis and see what happens. I don't know if we have any updates on that. Joachim, do you know anything about this, or are we not sure?
No update from our side. I
No updates.
have to apologize. I hadn't time to test anything.
That's okay. That's okay. It's just
still on the list.
Okay, so no updates from Intel, and you guys haven't had a chance to test anything. All right, that's fine. Just trying to stay on top of things here. Well, so if you guys haven't tested this, do you have a workaround or something that you've implemented, or?
Right, yeah, we have the workaround where we just force the tool to use the right block RAM.
Okay, gotcha.
What is called M20K, or the other
you
type
forced to use the M20K instead of the MLab. I see. Yeah, I mean, my concern is just, it seems to be a problem for this particular location, but I think there's other spots where MLabs are being used. So I'm not sure if we might get bit by this somewhere else, unless we're forcing it to use M20Ks everywhere, which I don't think would be very good for a resource.
Definitely a possibility. So. Yes, we did not notice any other problems so far, but you're completely right.
Yeah,
we simply don't know. Might be there the problem somewhere else. Simply not hitting it. I would
suspect that if we did run into this issue somewhere else, we would definitely be seeing weird behavior somewhere. So it seems weird that it would be, specific to this one particular instance, and that everywhere else hasn't been an issue. But I don't know. Something funny is going on. Anyway, if you guys have a workaround, I guess that's that's not much motivation to experiment with that if you have 50 other things to do. All right. Well, hopefully we can get to the bottom of this at some point. Okay, let's see. Moving on, priority flow control. So we're starting to take a look at priority flow control in Corundum. Basically, starting from the wire and working our way up, there's a bunch of stuff that needs to be implemented for this to work. I don't know if anybody here is familiar with PFC and some of the stuff that, you know, traditional NICs do, but any details that can be filled in would be great. Let's see, in terms of the hardware, there's a bunch of stuff that needs to be done. I think Antonio is working on the PFC pause frame handling and pause quanta counter implementation, which basically will sit near the max. But there's several other things that need to be implemented as well, and one of them is the per TC queuing that's needed in the transmit direction, such that the traffic classes can be kept separate. And this is one thing that's been, you know, kind of on the back burner for a while. You know, how might we do this? Now that we've started looking at the switch implementation, I've actually gotten a few ideas on what we might be able to do here. So the queuing, the IBM Prisma switch architecture paper that a couple of the papers we've been looking at have referenced presents a pretty interesting idea about memory management. The idea is to use FIFOs to store memory addresses, and then, oh, hang on a second. Basically, the idea is to use a FIFO to keep track of free memory addresses, and then you can, as you're putting stuff into the, you know, larger memory block, you don't just write it out sequentially, you write it out using the memory addresses that you've popped out of this free address FIFO. And then you can use much narrower FIFOs to store those addresses for, you know, reading the data out of the main FIFO. So the great thing about this is you don't have to statically partition the memory block that you're using for the FIFOs into, you know, 4 or 8 or whatever, you know, fixed size pieces. The different traffic classes or different ports, they could use varying amount of buffer space based on traffic conditions and whatnot. And this can be enforced, you know, at the scheduler level or something instead of in the actual FIFO. And that also means that if you don't use all of the implemented TCs, then they don't consume any, you know, memory overhead. Like if you have 4 TCs implemented in hardware, but you're only using 3 of them, for example, you know, you're not wasting a quarter of the memory. So I'm looking into implementing this basically for the main transmit and receive FIFOs in Corundum, such that they can efficiently handle multiple traffic classes and also multiple ports. So that's going to be good. We now have a relatively efficient technique, I think, for making this work. So at some point, hopefully soon, I'm going to start chipping away at this and getting that implemented. I actually have a...
Hello, Alex.
Yeah.
Can you hear me? This is Jesus from
Yeah,
Chile.
I can hear you.
We are working on PFC. So Antonio couldn't attend today, and I am here just to report that we are progressing, just identifying the modules to implement all the functionality you mentioned before. And I think this idea is interesting, the one of implementing the per TC queues.
Right.
Because
yeah.
I have one question. So you assume we use logical FIFOs, just storing the addresses of those packets that are being stored per each TC class, TC FIFO, I think. So these queues, let's talk them as logic queues, will be easier to manage. So we have the physical packet stored in the TX and RX FIFOs that we have now in Corundum, and we use the new logic ones, which are, as you say, narrower, to manage the traffic classes and the packets stored in them.
Right.
So the issue here is because we will need to do the scheduling of these queues to decide which of them will send a packet, will forward a packet at each moment. So I think that this decision needs to be done on the narrow FIFOs.
Yeah, exactly.
So we need to have a pointer to the physical FIFO and be able to access the second, the third, the fourth packet in that current FIFO queue in Corundum to get this packet and forward.
Right. So yeah, this is part of just the overall, integration of PFC support into Corundum. So the idea behind the per TC queues is you're going to have one of these kind of internal queues that's just keeping track of memory addresses per TC. So you can pull whatever, you can only pull packets out in order from a given TC, but you don't have to pull the packets out in the order that they were in queued, if they were in queued from across different TCs, if that makes sense, right?
But the order is defined by a scheduler on the on the um, on the new logic TCs we are going to implement. And these pointers allows us to access not the first one in order, but the third, fourth, and fifth, just in case. I mean, if the first packet in the FIFO is from TC0, the second TC1, the third TC2, and the TC2 is the one selected to forward a packet, then we will need to access the third packet.
Right. So the idea behind this is inside of the actual kind of backing memory, if you want to call it that, where you're storing the actual packet data, they're not stored in any particular order. They're going to be stored in basically a random order, because the idea is that you're not storing each packet contiguously. What you're going to do is you're going to store each cycle of the packet separately in the memory. So if you have, say, a 512-bit wide interface, one cycle is, 64 bytes. So the memory will be 512 bits wide. And then for every 64 bytes of the packet, you would pull another address out of this free address FIFO. And that could be just randomly throughout this memory. And then you put those addresses in the per TC FIFOs. And then when you want to send a packet from one of the traffic classes, which is basically going to be the highest priority traffic class that's enabled and has data to send, then you can just pull the memory address for a piece of that packet and then read that out of the internal memory.
Okay.
Does that make sense?
Understood. Yeah.
Yeah. So as a result, you can only access the next packet for each TC.
Okay. Yeah, I was confused about if you map the logic TC queues on the current FIFO queues, a FIFO still has an order, right? So
right.
But now it's clear. You have a pool of packets and you get whichever you want.
Yeah. Exactly.
Depending on the traffic class you are processing. Okay, now it's clear. I will take a view anyway to this IBM.
Yeah, I posted links to a lot of these papers in the Zulip. Yeah. Yeah. So this paper should be in there as well. So they have some nice figures and whatnot that talk about this particular memory management technique. And then it's also discussed in a couple of the other papers as well. I think the saturating the transceiver bandwidth paper also discusses that, but not in as much detail as the Prisma switch paper, I think. So yeah, and if somebody was having an issue with one of those papers, like it's on IEEE Explore, but they couldn't download it for some reason, even though the university had access to it. So if you have any issues with that, let me know, and we'll see if we can sort that out.
Yeah, anyway, the IEEE Explore, right? Yeah. Thank you. Anyway.
Right. Yeah.
Continue. I will take a view and discuss later.
Yeah, sure. All right. So that's the, I think about rounds it out for the PFC portion of the discussion here, unless there's anything else to add. Okay, so moving on, the AXI virtual FIFO that I've been spending far too long working on is actually starting to show some signs of life here. I've tested it in the hardware on an Alveo U200. It seems to be working. I've not tested it extensively because there's a couple little odds and ends I need to fix up to make it easier to test. And I need to finish the reset implementation, basically, because with a lot of clock domains, you also have a lot of reset domains, and coordinating all of that such that if one domain gets reset, independently of the others, that everything gets handled appropriately. So still got some work to do there, but hopefully I'll be getting that squared away soon, and then that'll go into the Verilog AXI repo. Yeah, so the idea is to support operation at 100 gigabits per second with all possible packet sizes. So that means, you have to merge together a couple of memory channels, either, maybe 2 of DDR4 2400 or 3 or 4 HBM channels. So on the U200, that's going to be using 2 channels of DDR4 2400. And yeah, so at this point, all of the encode and decode logic is working, and it's properly striping the data across, 2 FIFO or 2 DDR channels, and then putting the read data back together and reassembling the packets. So that's pretty good. And this also is storing some metadata along with the packets. I think 32 bits or so across the TID, TDES, TUser, etc. fields. So makes things a little bit easier to deal with. All right, so that's that. Let's see. Another thing that I'm thinking about doing is holding a, so getting onto the switch design stuff. I'm thinking about holding a meeting that alternates with the Corundum developer meeting, just focused on the switch. So same time in Zoom room as the current meeting, but alternate weeks. So this week is the Corundum developer meeting. Next weekend will be a meeting more focused on the switch design. Because at this point, there's a lot of brainstorming that needs to be done, and I think we can probably start getting into some of the nitty-gritty of building the switch in a bit more detail. So anyone's welcome to join if this interests you. We'll see how it goes. Maybe we'll just keep it as part of the Corundum developer meeting, long term. Maybe we'll keep it separate. We'll see. But that's kind of what I'm thinking. At least give an opportunity for myself and the couple of students that are going to be working on the switch to collaborate, more directly. Let's see. So moving on into some of the some more details on the switch. So mentioned this before. There's 2 different research groups that are potentially interested in an FPGA-based packet switch. Not just interested in using it, but interested enough to help build it. And they're planning on sending a couple of PhD students to UCSD this summer to write some code and work on stuff. So should be fun. And the idea here is to build a switch with a reasonable port count that'll operate at up to 100 gigabits per second. Probably going to start out with just standard Ethernet switching, but we do need to support traffic classes for both PFC and TSN. So there's definitely a question of how to do that efficiently on FPGAs. So again, if anyone is aware of any useful references or reference designs or anything that we can take a look at, that would be great. But for the time being, I've just been looking at whatever papers that I can find online relating to FPGA-based switches. So I know that previously I mentioned some papers that I found from Wayne Luke, and a couple of them involved this guy Filipos. I actually exchanged a couple emails with Filipos asking about a couple of their switch designs, and basically the gist of it is a couple of their kind of more interesting, more optimized designs actually don't seem to be super appropriate for like Ethernet traffic. They were targeting an environment where you have a very large number of small, consistent sized packets, which is definitely a slightly different use case than an Ethernet network where you have a wide variety of packet sizes. Maybe you don't have a huge variety, but you got some packets that are 64 bytes, and some packets that are 9K or 1500 bytes or something, and you have to deal with packets of significantly different sizes. And looks like some of these switch designs won't work very well in this particular use case. So as a result, I think kind of the current direction that I'm thinking is going to make the most sense is a combination of 2 papers. Originally, I was just looking at this switch fabric design on FPGAs paper that talks about their GCQ switch architecture. But from reading over that paper, it looked like there was a lot of details that weren't really elaborated on. So I was scratching my head over, okay, how do they do this? How do they do that? Not sure. But they were referencing this other paper that's this microarchitecture of a high radix router. And this one is the paper that proposes kind of the hierarchical crossbar design and spends a lot of time talking about the scheduling and whatnot of, that type of switch design. So between these 2 papers, I think we have a pretty good picture of how to build a, hierarchical crossbar, buffered crossbar design on an FPGA. The first one kind of gives you the kind kind of a deep overview of the architecture and the scheduling. And the second one goes into more detail in terms of how to optimize this to run efficiently on FPGAs. So putting those two together, I think we might be able to make something work. So I mentioned this before, kind of the hierarchical approach seems pretty promising for the switch fabric itself, but we might be able to extend that a little bit because we also need to do route computation. And in a lot of these switch designs, they're just focused on the fabric. So it's assumed that all of the packets that you're getting in, you know where you're going to send it. But we need to compute that. And the route computation component is going to be based on, the packet rate and not the data rate, right? Because you're going to be looking at the headers of each packet, not the whole packet. So how often you're getting a packet is the most important factor here. So if you build route computation logic that works at 100 gigabits per second, right, which is around 148 million packets per second, if you're using lower speed ports like 10 gig or 25 gig, it doesn't make sense, I don't think, to use that block as is for each individual port. It's not going to be very efficient. But what you can do is aggregate, multiple lower speed ports and then share the route computation block across multiple ports. So if you take, say, 4x25 ports, aggregate that up to 100 gig, well, that looks the same approximately as a 100 gig port, and it's running at the same packet rate, and you can, reuse that route computation block, and it should be quite efficient. So what I'm thinking we do is we build sort of two components. We have the core switch fabric, which maybe presents 100 gig ports, and then we build a kind of a per port module, which has the route computation logic and supports either a single port at 100 gig or maybe 4 ports at 25 gig and does the aggregation. And then we can mix and match those connected to the crossbar, because it's very common to have, like in a multi-port 25 gig switch, to have like a couple of 100 gig uplinks. So if we aggregate the 25 gig ports up to 100 gig internally, then that makes the design of the crossbar, more straightforward. We just have a bunch of, straightforward 100 gig ports. And then if we do this, potentially you could even build these port modules such that you can dynamically switch between single 100 gig port and 425 gig ports. But we can revisit how to do that later once we get the rest of it working, because that could potentially be a useful feature as well, being able to mix and match port speeds kind of at runtime. I know there's a lot of existing switches that can do that. All right, so the other thing I took a look at as well is a little bit of kind of back of the envelope calculations in terms of the actual switch fabric. And the switch fabric design on FPGA's paper uses RAMs for switching, which includes a speed up factor of 3 or 4, depending on the device they were targeting. So I think for the higher end device, they were getting a speed up of 4 using 40 megahertz for the lower speed clock and 160 megahertz for the higher speed clock. But I think they were just running at 10 gigabits per second. So if we're running at 100 gig, I think the computation is going to be a little bit different. So I went ahead and ran through some numbers on this just to kind of get a feel for what might be reasonable. So for 100 gig Ethernet traffic on a 512-bit bus, in order to get the full throughput at all packet sizes, you got to run it at around 280 megahertz, something like that, which is pretty fast. But if you pop that up to 1024 bits, that actually drops down to about 164, which is actually looking like a pretty reasonable number. I took a look at the data sheets for the UltraScale Plus. The Fmax for the block RAMs is 737 megahertz. Now, that being the Fmax, it doesn't mean it's going to be easy to write logic that can run anywhere near that speed. So, we'll see about that. But that does give you kind of an upper limit in terms of how fast you might be able to go. So if you want to do, say, a speed up of 4, that means you got to be below, around 184 megahertz or so. If you want to do speed up of 3, then about 245. Both of these numbers are below 281. So if you run it with 512 bits, you can really only get a speed up of 2. And then the high speed logic has to run at around 600 megahertz, which is, it's probably doable, but 600 megahertz is pretty fast, and the 2x speed up is not amazing. So looking at the numbers for 1024 bits, you might be able to run that at maybe 170 megahertz, a little bit faster than 160 or 164. You need a little bit of headroom there. 2x speed up on that would be 340, which is actually quite reasonable, right? The Macs are running at 322, so 340, a little bit faster than that. Should be possible to close timing there without too much difficulty. 3x takes you to 510, which, you know, that is pretty fast, but timing closure of 500 megahertz or so, I think would be a reasonable thing to do. 4x speed up puts you at 680. So I think that would be hard, but it might be doable. And it's at least below the BRAM Fmax. So I'm not sure what speed up factor is going to be appropriate, but I think running with a 1024-bit internal interface into the crossbar is going to be the way to go for 100 gig traffic. That's kind of the conclusion to draw from this at the moment. And we can certainly start taking a look at what the fabric itself might look like, and maybe run some test designs on FPGAs and whatnot with some of these ideas. So, and just to see what might make sense. Not sure if we have any input on the switch design. I think my next slide here is, moving on to some of the other stuff. Does anyone have any questions or comments on the switch at this point? No? Okay. So I'll move on to a couple of these other points here. So there was some talk about doing stuff with Zynq devices. And SoC devices, they have additional interfaces that are potentially useful to expose to the application section. So if you're running on something like an Alveo board where you just have PCI Express, I mean, everything interfacing with the host goes over PCI Express. So there's really isn't much to expose beyond the PCI Express interface and DMA and whatnot, and like the memory interfaces. And, that's about it. But on an SoC device, there are lots of various AXI ports. I don't know if you guys have ever looked at the TRM for Zynq, but there's a lot of stuff in there. So potentially it would make sense to expose some of this stuff to the application section. For example, you might be able to access the SoC directly via AXI without going through the DMA subsystem. Or there is, I think, on Zynq devices, a couple of different like cache coherent ports as well. So, something like that could potentially be connected. So what interfaces would be the most useful to add? Kind of the somewhat trivial one is an AXI interface into host memory. At least on the Zynq, we can just point that at another one of the AXI ports. On PCIe versions, eventually that could get merged into the DMA subsystem. Some point I'll put together like an AXI slave DMA client that operates similar to the Xilinx AXI bridge. And then that would work on both. So that's definitely something that we could consider. I'm not sure if there's any other interface that makes sense. And also another potential option is to put in an interface that goes the other way, right? An AXI that's where the ARM cores are the master feeding into the programmable logic. That could also be an option. I'm not sure what makes the most sense. I know Tracy's been working with this. I'm not sure if Tracy has much input or.
Yeah, I mean, the big thing I was looking at is the address space, right? Ties in with the DMA, second bar, multiple PCI interfaces, trying to come up with a unified view of all data. The thing I'm doing right now, I'm trying to wire it up with a direct AXI interface into the cache here so that the ARM cores can do some packet header processing. But definitely want to be able to use 4 gig on the PS and the 4 gig on the PL side. So I haven't figured out how to, what the best approach is yet. Just going to keep kicking around for this.
Okay, so you're definitely using the cache coherent interface. Okay.
Yeah. And you run into some funny things like on the cache coherent side, you're limited 64-bit bus, match the cache lines, versus 128. You can have, I think, up to 128 AXI interfaces directly into the DDR controller. So that's why I said trying to find the balance there is bit of a trick.
Yeah, I noticed there looks like there was something else weird about some of the cache coherent interfaces in terms of the address translation, I think. Like it isn't translated or something. I haven't taken a super close look, but I
Well, that
remember
ties
seeing
into
some
this
note
whole
about
thing
this.
of how do you do addressing, you know, as you merge all these different DXI addresses.
Right, yeah.
Current DMA, I'm still toying with the idea of using some of the other by8 interfaces of the card for maybe a secondary interface. But then that just opens up this whole Pandora's box of translation and addressing across the second.
Yeah, I guess there's two different aspects if we're talking about, you know, multiple address spaces, right? One of them is you might have to translate it somewhere, but another one is how do you even identify which address space, you know, you're dealing with? So in some cases that's more straightforward. In other cases, there's not necessarily an obvious, you know, really clear path.
Yeah, so what I'm trying to do some security processing with packets, and you know, my goal is to just peel off the aspects of the headers that I really care about, and sticking those into the sync space while holding the packets themselves in the FIFO or DDR or the PSI, but being able to make a thumbs up, thumbs down decision to release or destroy the packets from arms. So you've got to play on both sides, but I think your applications can be aware of the different addresses. I don't think you need a single unified space. That's my application. I don't.
Okay. Well, I mean, I guess we can also, you know, take this over to Zulip and think about what might make the most sense here, because we can certainly add some more AXI interfaces. It's just a question of what's going to make the most sense if we're going to thread that through. And then also, there are other kind of SoC style devices, right? Like you have the Xilinx has their Zinc devices, but Intel also has the hard processing subsystems on some of their Agilex devices and whatnot. And then I think also Xilinx, you have the Versal devices as well, which tend to have ARM cores. So I'm not sure if there's like kind of a common denominator we can draw out of these that makes sense to put in.
Agreed.
But even if there isn't, you know, we could always add a couple of auxiliary buses that you can just hook up however you need on a particular system. Anyway, let's see. So that is kind of the idea behind making some additional connections to support the application section when you're running on a Zinc in terms of some of the kind of non-standard interfaces that are provided by the hard processing subsystem. And I guess I should mention this is not necessarily limited to hard processing subsystems like you might have on a Zinc, but maybe you want to do a soft processor for whatever reason. You know, it's like a RISC-V. You could potentially take advantage of some of these connections as well. But one thing that Tracy mentioned is, well, what if you want to use both PCIe and Zinc device at the same time? Well, that brings me to this next slide here. How do we do like multi-heading support, right? Where you could potentially have concurrent access to Corundum from both, you know, a hard processing system as well as PCIe. You take something like a 250 SoC that has 16 lanes of PCIe and it has a built-in, you know, Zinc SoC. Well, how do you, you know, use both of these at the same time? And for a while I was like, man, there's probably a way to do this, but haven't really come up with a good solution for this. But recently I just realized, well, why don't we just give the Zinc effectively some SRIOV virtual functions? So for SRIOV, each virtual function has its own view over the system address space, right? Because you're going to have the IOMMU in there. It'll be, you might be passing the VFs through to different virtual machines. So each VF, you know, the same address could end up going to different things depending on which VF you're accessing host memory from. So kind of my plan for implementing SRIOV is you have multiple VFs. You can then associate queues with the VFs. Once that takes place, then the driver running inside of that VF, it'll write out descriptors. that'll be associated with the queue, and then each descriptor will code for some operation, right? To send a packet, to receive a packet, whatever. So we need to keep all this stuff straight such that when that operation actually gets executed, it will it'll be done in the context of that particular VF, and all of the associated PCIe traffic will have that VF marked. So if we can keep this kind of arrangement, then this should be a pretty straightforward thing to do. So the idea in this case is you'd have kind of your master physical function, which would actually have control over, which queues were associated with which VF. Then you would talk to the driver and use that to associate the queues with various VFs, and then the drivers can use those queues. So the idea with Zinc is we basically have a non-PCIe VF, or a couple of them, which would be connected to the Zinc PS. And what we can do in this case is basically treat it exactly the same as, another PCIe VF. It's just only visible to the Zinc device, and any accesses that VF makes would be appropriately tagged such that they would be carried out by the AXI DMA components facing the Zinc instead of the PCIe DMA components facing the host. So that's kind of my thought, and I think this could, once we get the hooks in here to support SRIOV, this would potentially open up some interesting avenues on like the 250 SoC and like the ZC106, anything that has both the hard processing system and a and PCI Express interfaces. I guess this is slightly different than just connecting up a couple of AXI interfaces to the host, but I guess another thing that dovetails into this as well is that when we have the RAM bar working, right? So we have, in the current setup, we have basically 3 PCIe bars. We got bar 0, which is for the controlling the NIC, bar 2 for the application, bar 4 will be for accessing on-card RAM. Potentially what we'll be able to do is mix and match buffers between host memory and the on-card memory, and potentially it'd even be possible to expose the like the Zinc's internal address space as part of that RAM bar as well. And if you set that up right, then it should be possible to mix and match buffers across all of these different address spaces effectively inside of the descriptor queues. And then the DMA engine will do the right thing based on whether the address falls into this bar 4 range or not. Because the idea is that you would actually read the bar configuration out of the PCI Express hard IP core, and then you can, check the target address based off of that and send it to the appropriate DMA engine. So we put these two things together, and this could allow you to do some interesting stuff where you receive packets into buffers that live in the card, like in the either into the PS DRAM or PL DRAM, and then you can point the Zinc cores at those packets, and they can do some processing. So I'm not sure if there's anything else that would need to be done here, but yeah.
So just, you and I went back and forth on this. And so my takeaway is setting up the SRIO VDFs. Really, all you're doing then is making the downstream components, or I guess NIC side components, aware that there's going to be multiple queues, right? But Zinc accessing that is going to be through the AXI interface, right? We're not talking to the IP. And the DMA then is aware of the address space, so that if you send a descriptor back an address that's in PS memory space, right? That's going to be intercepted. I guess what I'm trying to chase is there's really no exposure of this idea of VFs. Then, I mean, we could expose it, I guess, onto the PCIe host side, but in the simplest form, there would simply be no visible VFs to the host, right? It would just be setting up the ability to have those extra IDs for queue management.
Right. Yeah. So in this case, I'm putting VF in quotes because, it's not really PCIe VFs. It's just kind of using the same
Right.
the same infrastructure on the Corundum side. So I think I mentioned this before. It's like in the context of the core Corundum data path, we just need like an address space ID field. So in SRIOV, that would just be the VF number basically. So in this case, we would just have a couple of address space IDs that wouldn't correspond to PCIe VFs, that would instead correspond to, the DMA interface on the Zinc.
And if you were to create 4 actual Linux visible VFs, they're mapped to 4 different virtual machines or something, those would continue to work fine, and then you could still have a couple additional VFs for the Zinc side.
Yeah, exactly.
Okay.
Yeah, so that's what I was thinking. Like for SRIOV, you could have like I think 7 VFs, for example, on the ultra-scale devices. On the ultra-scale plus, I think it goes up to a lot more than that, 128, 256, maybe even more than that. I can't remember the number off the top of my head.
Sounds familiar.
You can support a lot of VFs. I think even some of the Intel ones will go up to like 2048. I'm like, how does that even work with the PCIe addressing? Or maybe it's not 2048. It's like 2047 or 2046 or something like that, because the PF takes up 1 or 2. Anyway, but yeah, the idea is that you would support like a couple of additional VF numbers that don't correspond to PCIe ones that correspond to the Zinc ones. So you could have, 1 PF plus like 7 VFs plus 1 or 2 Zinc VFs, basically. And then they could all share the same data path.
I'm just trying to figure, would that allow us to take a descriptor out of one? Like if a packet coming in and I'm sending it to a ring that's in the Zinc VF, I do some processing on, then we assign that same descriptor to a ring on the host and have it retrieve that packet?
That's a good question. How do you hand packets from one to the other? Because I guess you'd want to do that ideally without copying the packet, or maybe you would want to copy the packet. I mean, would you want to have the host access the packet where it is in the memory on the card, and pay all of the PCIe round trip times for all of those accesses, or would it make sense to DMA the packet from the card back to the host?
From one ring to another ring on the host? I don't know. Just things you got to ask, right?
Well, right, yeah, because it's just a question of how you would transfer that information, right? Because the host is going to allocate its own buffers basically out of the host memory or wherever. So unless you change something fundamentally about how the descriptors work, you almost have to recopy the data. But that might make sense to do anyway, because whenever you go over PCI Express, just having the host directly access memory on the card, while it's possible to do that, you're going to be paying a pretty significant performance overhead. So what might make sense is to have like some sort of a loopback support, basically, where you can send a packet from one VF to another VF without it going out over the wire. And if you can do that relatively efficiently, then that might be the way to go. And then if you're talking about security stuff, now the host doesn't need to be aware of anything going on in the Zinc, right?
Right. Correct.
It's not even doesn't need to be aware. If it doesn't have visibility, it would still work. That's kind of the whole point with the VFs is you want to isolate the VMs from each other and potentially isolate them from the host as well. So anyway, that's kind of my idea here. I think it's going to be some time before we actually get to the point of all of the pieces being in place for this to work. But
well, the other thing too is, what about being able to access buffers and descriptors between cards? Just fun. Memory.
You say that again? Accessing buffers and descriptors between cards?
Sure, if you stick 6 cards in a box, right, and that, and I got thinking like the 250 SOCs got 40
Right.
memory, right? So how would you move information between cards?
That's a good question. I mean, I think there's two straightforward paths that you could take. One of them is to bounce everything through host memory, and the second one is to use peer-to-peer DMA. Depending on the host system, I think in some cases peer-to-peer DMA might not work, or might not be possible, depending on how things are configured. So you might need to bounce stuff through host memory. But the other question is that if you do, say, bounce stuff through host memory, or you do peer-to-peer DMA, how do you communicate, when some operation is complete, right? Because the interrupts, for example, I think those are basically just going back to the host. So how would you have like one card interrupt another card and say, hey, I've just performed a particular operation? I guess you'd have to use peer-to-peer DMA for that. That would be the only way that would really work, unless you have the host involved, right? You send an interrupt back to the host, and then the host driver says, oh, that isn't actually for me, that's for this other card, and then it performs some operation against that.
Yeah, I don't have an opinion. I just have questions.
Yeah, I mean, it's something to think about. I don't know what's necessarily going to make the most sense if you wanted to implement something like that.
Yeah, I was looking at an application a while ago about providing some content, and it just made me think that sometimes there's value in going back to the host, but sometimes there's value in staying on the card or going to a secondary card as opposed to bouncing it through the host and the OS. So I was kind of had one thought on both sides of the fence.
Right, yeah. Yeah, you just have to figure out what the right, if you are going to go from one card to another, I'm not sure. I've thought a little bit about what's necessary for, like peer-to-peer DMA to work, in terms of you need to be able to handle, full size PCIe operations from the card end, because if the CPU is issuing an operation, it's only going to be 32 or 64 bits. But if another device is issuing a DMA operation, that's going to be much larger, and you need to be able to sync that, into DRAM or source it from DRAM on the card. So that's one aspect of it. But then the other aspect is, how do you do, all of the other coordination that's going to be required, right? How do you do interrupts basically from one card to another? Not sure about that. So potentially could be an interesting discussion for a different day once we have a more concrete idea on what you might want to do. But yeah, getting back to the multi-heading thing, there's a lot of groundwork that I'm going to have to lay for this to work, and probably the main one is just to have some sort of address space ID. Originally thinking VFID, but maybe I'll think up a different name that's associated with basically all of everything that touches memory is going to have to be aware of this somewhere. So the queues are going to have to be assigned there, and that's also going to have to be connected to the DMA engines and threaded through probably all of the AXI Lite interfaces as well. So lots of modifications to make, but this does seem like it could be a pretty promising direction to take things in, and could open up some pretty interesting capabilities. All right, let's see. I think I had another thing I wanted to mention here. Oh, right. Yeah, queue management consolidation here. Okay, so in the current version of Corundum, we have like 5 different types of queues, right? We got TX queues, RX queues, TX completion, RX completion, and event queues. But there's just a single descriptor fetch module and a single completion write module that then are responsible for dealing with all these different types of queues. When I was working on the batch completion write support, managing this has been a little bit difficult, right? The module I was putting together for doing the completion write back, I was having trouble figuring out how to connect that to multiple queue state storage blocks. So what I ended up doing for the kind of prototype I was putting together is just I put down 3 of them, which is not good for the logic resource utilization, but potentially it could be good from a performance perspective. But it got me thinking, is it really necessary to keep these different types of queues separate? Maybe it makes sense just to have descriptor queues and completion queues, and then you can just allocate however many you need of, whatever type, and configure the hardware appropriately. Because even as of right now, we have fields in all of the queue state to support, pointing any transmit queue at any transmit completion queue. Well, this would just mean we can point any descriptor queue at any completion queue, which could potentially make things a little bit easier to deal with. And it could also be useful, in the case of where you have a bunch of VFs, if you need, different numbers of event queues or different numbers of completion queues, depending on what's going on. So there could be some pretty significant advantages of doing that. But there are potentially a couple of downsides. So one of them is performance, right? I mean, if you're sharing resources, then you have the potential for contention and whatnot. But the current implementation is shared, so consolidating stuff, presumably the performance wouldn't be any worse the way it is right now. But I mean, if you're making a change, if you have the potential for better performance, that could be something to consider. The other question as well is efficiency. So some resources might be wasted if you're going to collapse all this stuff down, either queue state and or the scheduler state. But another question is, is that really a significant problem? For example, I think a lot of the current designs have something like 8192 transmit queues and 256 receive queues and like 64 event queues. So if you were to consolidate all of that, you would probably support, 8192 queues. You have 256 receive, 64 event, and then the balance transmit, which means you're going to waste a few of the descriptor queues because the transmit queues and receive queues, you have one of each, descriptor and completion, but the event queues are only completion queues. So, you waste a little bit of queue state there. And then your scheduler state probably has to support 8192 because that's a power of 2, but you don't have 8192 transmit queues. You're going to have, 8,000 or 7,900 or something like that. But is that really a significant problem, right? The trade-offs, if it makes it more flexible, maybe that's a reasonable trade-off to make. Not sure. For smaller queue counts, if you're doing like, 256 transmit, 256 receive, something like that, maybe that's less of an issue, right? Because if you have 256 transmit, maybe you design your scheduler for 256 and then receive. Maybe you have, 128 and then you have, a few event queues. Not sure. But consolidating like this could potentially make be more useful when you have a smaller design with a smaller number of queues, because now we don't have all these queue types. So this is something I'm thinking about. I'm not sure if anybody has any thoughts on this. I know potentially the folks at MLE might be interested in something like this if it reduces the footprint of the overall design, which would make it easier to fit on smaller FPGAs. I guess another aspect to consider as well is that getting back to the performance point, if you just have one copy, you might be able to throw a few more logic resources at, improving the performance, increasing the number of packets you can handle per cycle, or, reducing the number of cycles per packet, things like that. Which if you have multiple copies, it doesn't make sense to spend a logic resources. Another component to this is that maybe it still makes sense to keep the event queues separate from the completion queues. I think I ran into an issue along these lines at some point when I was working on some of the updated descriptor handling logic, that there could potentially be a deadlock issue between when you're generating a events to try and flush stuff, or when you're trying to flush stuff out of the cached table for the descriptors that need to be written back, and you have to generate events, and then those events need to allocate entries in that table. That potentially creates a deadlock. So I'll have to figure out if there's a way to avoid that. I think it's possible. I think that's less of an issue than I think it might be, but that sort of thing is something to consider. So maybe it makes sense to keep that separate. That would alleviate some of the issues if the event queues were separate. Another question is that if you're moving on to something like RDMA, having more flexible queuing infrastructure might end up being significantly more useful. But I guess we'll see about that. But yeah, this is a change that I'm thinking about making. I don't know if anybody has any thoughts on that. I think that about rounds out my presentation for today, though. Let's see. Yeah, that's the last slide I have. All right. So does anyone have any other questions or comments? I know we've had a few kind of interleaved in the presentation, which is good. Nothing? No questions? No comments? No concerns? All right, well, I'll shut down my slides for now then. Anything else that people want to discuss? I don't know if there's anything we need to discuss about the switch, Carlos, or if MLE has any questions, Joachim, or if anybody else has anything they want to add. I don't want to put anybody
Hi.
on the spot, but
Well, I haven't checked anything else about the Switch so these days. So I
Okay.
think maybe we can wait for the next month for the first official Switch meeting.
all right.
I
Yeah,
also want to. You mentioned that you are going to work on the share buffer implementation for the FIFOs, I think,
right. Yeah.
for the at
But
least
at
for the
some point,
PFC.
maybe not in the next couple of weeks, but at some point, I think that would make a lot of sense to use that that setup there.
Okay, just to let you know that I think because they are probably going to be used at the Switch.
Yeah.
Maybe I can help with its design and with the code for it. So you can come
Yeah,
with
possibly.
me. Okay.
Yeah, that might make sense. And then for the Switch, I think it'd probably make sense to, I think we mentioned this before, is to start putting together some just simplified test switches just to see kind of how things look from an architectural perspective. So
Yes.
one thing I've noticed is that the first version of anything that you build is not necessarily going to work very well, right? You learn a lot from the first, maybe even a couple of versions, and then you use that to refine the subsequent ones. So
Okay, makes sense.
that's kind of how Corundum itself has been working. I wrote the whole thing, but a lot of the modules are complete crap. So now I got to go through and rewrite them to improve the quality, improve the performance. So we're going to build a switch and make it really good. We're probably gonna have to do the same thing. So first pass, something simple, make it work, and then iterate on there. But what do you think about some of the figures that I put up in terms of the speed up, right? So if we go for a 1024-bit interface at about 170 megahertz or so, 170 megahertz, if we run the route computation logic at 170, that's actually going to be, I think, pretty easy from a timing closure perspective. And then if you're dealing with 1024 bits at a time, it's 128 bytes. So you get the whole packet header in one cycle.
Yeah.
That could potentially simplify things. Not sure about that. But yeah, I'm not sure how fast we're going to be able to run in terms of those sub switches. I think trying to push those anywhere near the BRAM Fmax is going to be hard.
Yeah.
But it looks like there are potentially a couple of steps there, right? 340 megahertz, I think would be very doable. Much more so than 600. And then we do have a couple of intermediate steps perhaps. So we got
I
some
think
design
so.
space to explore.
Yeah, I don't really know how. So yeah, for how can you parameterize the computation model to just take 1 or 4 ports if we are going to do this thing of the mix and match? I don't really know how we will do the design of it.
We'll take that one step at a time, right? We'll build it for one version, and then we'll work on it from there. Yeah.
Fine. Okay, fine.
You can come with us as well with GCLM for the switch. We can help. But once we finish the PFC, we will. I mean, we have some switch models in some of our simulators, such as the share buffer switch, and we can use this to validate the implementation just in case. Or
yeah, that's a good idea.
just
What kind of simulation tools did you say you're using?
Yeah, we based our simulator in a broken switch that is included in an NS3 simulator model. They use a shared buffer, and this is used in the Trident switch or even in the Broadcom Tomahawk switch as well. So we have
Okay, so you're using the
some
NS3
model.
simulator.
No, we are using our own, but our
Oh,
shared
okay, I see.
buffer switch microarchitecture is based on this.
Gotcha. Okay. Okay, so you
So
built
we
your
can
own
participate
simulator,
in
and then you
Yeah.
took the NS3 model of the Tomahawk switch.
Yeah,
and
basically
you've
we have
implemented that.
this microarchitecture where when packets arrive to the switch, they are stored in a shared buffer, and when we count the occupancy of the FIFOs and virtual channels in the ports, so that we drop packets when the ingress side is full. We have a piece of headroom as well, and we implement PFC in order to avoid this packet dropping
Okay.
when traffic burst appears. So we can simulate. Actually, we have a test bench for a 64 Tomahawk 4 switch, 10 gig, and we can use this as simulations just to help in the modeling of the FPGA switch model. If you think it's interesting, we can play with it.
Well, possibly. Carlos, what do you think? Is that would it be helpful to try to do stuff with their simulator, or you think it makes more sense just to stick to HDL simulation? Carlos, you're muted.
Okay, sorry. Yeah, I think we can, yeah, you can present us how it works. I feel more comfortable with the HDL thing, but maybe if you present us and we see that this is a good option, we can also move a step forward it. Don't know.
I mean, I think they're complementary, right? Because the HDL simulation, that's important for actually, testing the HDL code. And I think it makes sense to put some of these designs together in the HDL so you can kind of see how all the pieces need to fit together. But architecturally, it might make sense to, test things out in their simulator, because that's going to be, if that's what we're going to end up building, then we need to make sure that that it's actually going to work and get good performance, and it can be modified to support the more specific functionality that they need. So
At least to find a switch configurator that in a let's say large scale simulator and in a HDL simulator works and matches their behavior, and then you probably use the simulator to scale up and see how this works in a larger environment. But I agree that for small things it's better to use maybe HDL simulator just to see that everything is working. But I mean, we have this. It's not very accurate. We simulate at packet level, and we use logic queues, and basically the structure to control the shared buffer occupancy is based on a simple module, basically controls the number of leads that enter into the switch, and controls that all the ports are storing fleets there, and once the occupancy reach some occupancy, shared buffer occupancy, then we start to drop packets. So it's quite simple. But it's open. I mean, if you think it's interesting to compare the low-level model to this, the results we see in these simulations, we can help with what I mean.
Okay, for me, this is right. So maybe you can present us or present to me, or I don't know, yeah, shortly how it works to try to figure out how to start testing it. Yeah, do some tests and then try to reach something useful for the switch.
this would probably be a good thing to discuss in more detail, next week at the switch meeting, so we can go into
Yes.
more detail about what the simulator is doing and how how we might be able to divide things up. Because it's possible that the architecture that we're thinking about is going to be a little bit different from the Tomahawk device. I'm not sure. Maybe it's going to be functionally the same at a high level, but maybe not. Not sure. So, and then it's also a good question in terms of, you know, how much buffering do we need and whatnot. That's kind of an important question, right? Because the FPGA has a certain amount, and how you divvy that up, you know, maybe it has a significant effect on performance, maybe it doesn't. I don't know. So that's potentially something that that we're going to have to look into. And if we could look into that in, you know, kind of a high level simulation, that can direct, you know, the HDL.
At least the high level simulator allows us to tune the PFC thresholds. How to detect, bearing in mind that maybe packets that are packets that maybe are flying, and once we send the packet back, these packets are still flying. So until we stop the previous one, we will receive packet that will need to be stored in a headroom or another space. So
right,
having a lot of ports with this incoming traffic makes it more complex if the PFC doesn't react fast enough to block the traffic that is incoming. But anyway, this is an option that we can discuss.
Yeah, sounds good.
In the switch.
Yeah, let's well, if you guys have the time to tune in next week, then we can certainly discuss that in more detail.
Okay,
sounds good.
It will be the same hour, right?
Yeah, that's the plan. I figure if this time seems to be working for everybody, unless there's some, nobody's complained, so
Okay.
I'm assuming
just
that
to book
it's for everybody who's here, you know. Well, we got people all around the world, so you know, it's hard to find a time that works for everybody. So one thing I was thinking about doing at some point is like alternating meeting times between like 9 a.m. and 9 p.m. or something. So, you know, you're more likely to have at least one time that works for you.
Just to book in my agenda. That's fine.
Yeah, because I don't think we have anybody from like Asia on here at the moment, but or maybe we have one or two. I don't know. But yeah, I know there's been a couple people in like Korea or China that have been interested in working on Corundum, but I don't know if the meeting time works very well. If it ends up at like 4 or 5 a.m. or something, then that's kind of a problem. It's been a while since I've checked.
Well, then they don't want to work on it very badly, do they?
Yeah, okay. I guess you could make that argument.
You get 37 friends in China to show up. They can vote for the 2 a.m. meeting time.
Yeah, I also haven't sent a poll around recently either. Yeah. Anyway, this time seems to be working, so I figure if it works, we might as well just keep doing what we're doing instead of changing things up unnecessarily. So that's just going to cause confusion. All right. Does anyone else have any questions or comments? Definitely had a lot of discussion on the switch, but I don't know if the folks at MLE, you know, Joachim, if you have any questions about Corundum, anything we need to address?
No, not today.
Not today. All right. All right, that works. That works. Okay, well, if we're all out of stuff to talk about, then I guess we can adjourn the meeting for today. Oh yeah, Jesus, I think you wanted to talk about some stuff related to the setup there, right? You wanted to talk about that separately? Okay.
Yeah, I think Antonio is waiting now. Is just text me saying that he was in contact, so we can discuss with him.
Okay, yeah, sure. So if we're done with the Corundum stuff, then I'll go ahead and, you know, end this meeting, and then we can hop on separately and discuss that stuff.
Okay.
All right. Assuming nobody else has anything they want to talk about. Going once, going twice. All right, when is the next meeting going to be? Just FYI for everybody here. 1 week is the 6th. Wait a second. Hang on a second. Okay, so next week is the 6th is 1 week from today. So 2 weeks is the 13th, March 13th. So that'll be the next Corundum developer meeting on March 13th, and then the Switch development meeting will be on the 6th. Okay. Sounds good.
Okay, great. Thank you.
Bye-bye.
All right. talk to you guys later. Thanks for tuning in.
Thanks. Bye.
Bye. Thank you.